Let's begin our next lesson on Section 3, Molecules and Models. So we've done a really good job just kind of exploring atomic structure in our last lesson, and we're going to move on to the topic of bonding in molecules, and then of course in turn so we can understand that ozone hole, the focus of our chapter in the ozone layer. So we'll begin with a simple model. Let's just consider hydrogen and try to think about Lewis dot structures, or in other words just electron dot structures, and useful ways of predicting the bonding that's going to occur when atoms come together to make compounds. And we explored compounds when we talked together in our first chapter as a pure form of matter. Let's begin just understanding how we put Lewis dot structures together to represent their number of valence electrons, and we'll do so with period 2. So with your periodic table, again, just the same picture from before. Period 2 is the second row on our periodic table. So if we consider lithium in group 1A, we would simply write its Lewis dot structure by writing out its symbol and then a dot to represent its one valence electron. So I would see that written as lithium, and I can put a dot on any side, it absolutely doesn't matter. But any element, hydrogen, lithium, sodium, potassium, rubidium, cesium, or francium, a Lewis dot structure to represent its one valence electron just simply writes the symbol and the one valence electron to represent how many electrons are available for bonding, electrons in the outermost shell. If we consider beryllium, who is in group 2A, again with beryllium I would just designate 2 electrons. Notice how I'm putting one around each side of the symbol first. If I would model magnesium, I would just write its elemental symbol and I would place 2 dots. The 2 dots can be around any of the sides just so they're not partnered yet. We are hopping over the group B's, the transitional metals, and only focusing on our group A's, those who represent their valence electrons, known as the representative elements. We move to group 3A and we would have boron. Boron has 3 valence electrons. Notice how I'm putting one around each side first? Not partnered. And again, it would be true for any of those elements in that shared column: boron, aluminum, gallium, indium, thallium, and this is a not naturally occurring element yet named. They would have all 3 valence electrons. We would continue with the sample called carbon, 1, 2, 3, 4. Notice how I'm placing one around each side first. I could follow that same trend with the element silicon, placing 1 dot around each side representing the 4 valence electrons. Next door lives nitrogen, and finally we are now going to partner one around each side first, and I'm going to partner, and it doesn't matter where, but one of those lone electrons will now receive a partner, giving us 5 valence electrons. And of course you would predict phosphorus would follow the same trend: 1, 2, 3, 4, and then finally I start to partner the electrons. Oxygen, who lives in group 6A, oxygen would receive 6 valence electrons. I place a dot around each side first, and then I go back and assign partners. So I have 2 unpartnered and 2 partnered electrons. And of course sulfur, following our periodic trend, looks exactly the same as the oxygen Lewis dot structure. Fluorine, who lives in group 7A, would have 7 valence electrons, one around each side first, and then I go back and form partners. There are the 7 electrons for the elemental form of fluorine. And again, you would predict any element in group 7A would have 7 valence electrons to represent the group number that it lives in. And the noble gases, we see neon, argon, krypton, xenon. I'm out of room here, but I could just simply show the elemental symbol of neon. I'll have to put it up here because I don't have room on the slide. 1, 2, 3, 4, 5, 6, 7, 8. Everybody ended up to be partnered. Helium, of course, with its 2 valence electrons. With a noble gas arrangement, we are going to show that first energy level full. Let me kind of explain a little bit what we're doing. Lithium, 1 valence electron, beryllium, boron, carbon, and so forth. We have our group numbers 1A, 2A, 3A, 4A, 5A, 6A, 7A, and group 8A. Those representative elements represent the number of valence electrons. And why do we care as chemists? Well, we're about to learn that every atom on the periodic table wants to have the noble gas arrangement of 8 valence electrons, simply because it is the most stable arrangement. This is known as the Octet Rule, O-C-T-E-T, the octet, meaning 8. 8 electrons around the symbol. Unless, of course, you're hydrogen, and hydrogen's noble gas, hydrogen would just have 1 valence electron right here. Hydrogen's noble gas only has 2 electrons in that first shell. So remember, hydrogen with its 1 valence electron would only need to achieve 1 more to become a noble gas like helium. And so what we're about to discover is how atoms combine together, bonded to share pairs of electrons, so that when we look at that, it ends up looking like a noble gas. This atom of hydrogen with its 1 electron, this atom of hydrogen with its 1 electron, now share a pair of electrons in what we refer to as a covalent bond. We have made a simple hydrogen molecule. The formula, H2, a molecular hydrogen, 2 H's bonded together, and I'll add the word here, a single covalent bond, 1 shared pair of electrons. So what we're getting at is discovering how many electrons these elements down here that we drew for have open spots for bonding. For instance, this fluorine with 7 valence electrons, see this unpartnered electron? It's an open spot available for bonding when it forms a compound. Same with chlorine. Notice the oxygen, how it has 2 unbonded electrons or unpartnered electrons. These are what we refer to as open spots for bonding. They're going to look to achieve a bond here to create a shared pair to become like a noble gas. Fluorine has 1 open spot for bonding. Oxygen has 2 open spots for bonding, just like sulfur. What might you predict for the nitrogen? Notice how there is 1, 2, 3 open spots for bonds. If I could achieve a noble gas arrangement, I would look to achieve partnering those 3 empty electrons. And the trend continues. How many spots do you see open for bonding business in the carbon? Well, of course, 1 around each side. By achieving a shared pair of electrons, we could achieve a noble gas arrangement of having 8. So remember, when we share a pair of electrons, this line, this single covalent bond, represents a shared pair. 1 electron would come from another element that it's bonding to. Perhaps carbon wants to hook to hydrogen. Hydrogen with its 1 dot, group 1A. Hydrogen would form a single covalent bond, sharing a pair of electrons. Hydrogen now has 2. That makes it happy. It has 2 electrons. It's noble gas like helium. And this carbon would also be sharing those electrons. So we're looking at forming bonds with other elements to achieve a noble gas. Notice that I'm going to stop talking here about boron. Boron would want to be looking for, because now we're looking at metals versus nonmetals. And I want to be very clear in my chemistry lesson that nonmetals will share electrons, forming these covalent bonds. But when we move to the world of metals, we will learn that they form a completely different type of bond called an ionic bond, where they're actually losing or gaining electrons. So for our sake, in this particular lesson, we're going to stop the discussion when we move from the world of metals to nonmetals, and later in our course we will reintroduce how metals bond by losing or gaining electrons as ions. So we have learned how to write Lewis dot structures based on the group number they live in, and for those nonmetals, hydrogen included, the nonmetals, we are learning how to predict how many open spots they have available for bonding. So other than hydrogen, all nonmetals want to create an electron arrangement of the noble gases. We called this the Octet Rule. Now I say not hydrogen because hydrogen's noble gas is helium, and helium fills with 2. So to repeat, every element that's a nonmetal, here's hydrogen, it wants to have 2 electrons to fill the first energy level to be like helium. Boron, carbon, nitrogen, oxygen, fluorine, and neon, all of those nonmetals want to achieve the noble gas, and they'll do so by sharing electrons in what's called a covalent bond. The goal of nonmetals when they form molecules is to achieve the most stable arrangement, and we'll refer to this over and over as the Octet Rule. Now, knowing that hydrogen only needs 2 electrons, it's like hydrogen with its 1 valence electron has the opportunity to connect with just one position. So it could be, for instance, with a carbon forming a single bond. It could be, for instance, with a fluorine who had 7 valence electrons. So the 6 that are partnered with one another plus the 1 that was lonely could actually hook here and make a single covalent bond. The moral of the story is never ever select hydrogen to be a central atom as we start building molecules, because it only has 1 position to connect with. When we represent molecules with Lewis structures, we can consider a first example, such as water. We start to create a molecule where we have what's called a central atom, and the central atom serves to connect all of the other atoms back to it with a covalent bond, a shared pair of electrons. If we consider, and we'll just extend the page and start working this out. Here's a molecular formula for water. 2 H's and an O is a compound we're all familiar with called water. Now what we're looking at is, how does the 2 H's and the O connect to make a water molecule? And the answer is, we start building these molecules, I want you to think about symmetry. I want you to pick a central atom and build everything back to it. Thinking symmetry. Between 2 H's and an O, and understanding never pick hydrogen to be a central atom, that tells us that excuse me, we are going to select oxygen to be the central atom. How many valence electrons does an oxygen atom have? And remember, that lies in the secret here of the periodic table. Oxygen lives in group 6A. It has 6 valence electrons. When we draw the Lewis dot structure for oxygen, we will place 6 dots around it, and then we will discover 1, 2, 3, 4, 1 around each side first, 5, 6. We discover that we have an open spot left and right in terms of open spots for bonding. Remember hydrogen, it has also 1 valence electron. And so I place them so that when I connect, and I'll do it in green so we can see, when I connect the hydrogen electron to the oxygen electron, this is the very definition of a covalent bond, a shared pair of electrons. When I connect these two electrons with a single line, it's a covalent bond. And I'll add the word single because it's just simply one shared pair where oxygen has placed an electron into the same configuration as the hydrogen. So consider this in terms of how many electrons does the hydrogen have now total? Well, it has 2. One shared pair is 2 electrons. And remember, that's exactly the number that hydrogen wants because its noble gas is helium, number 2. Same story over here. This hydrogen has 1 shared pair or 2 electrons. These two are identical. But when you consider, I'll pick green, the oxygen also has an octet, 1, 2, 3, 4 of its own, and then a shared pair, 5, 6, 7, 8. This has 8 electrons, which is exactly what the octet rule says the oxygen wants. Oxygen now, if you consider where it lives, its noble gas that it just configured for is the neon, number 10. So by sharing electrons, I think I want 2 down. By sharing pairs of electrons, we've satisfied the octet rule. Oxygen has 8, and each of the hydrogen have 2 electrons in a water molecule. Now let me be clear, we've satisfied the octet rule, but we're not discussing the geometry of the molecule. What is its 3-dimensional shape in space? It's not a flat molecule at all. We might have even seen water drawn as a bent molecule, but I want to tell you that in a next chapter we'll talk about molecular geometry and start to get a feel of how they actually exist in a 3-dimensional world. Water is not a linear molecule, it's a bent molecule, but it does give me great insight into how the atoms connect together to satisfy the octet rule. So here we said a lot of things in our drawings. We said oxygen has 6 valence electrons, so we placed those 6 valence electrons around its symbol, showing us that it had 2 open spots for bonding. Each of the hydrogen had 1 electron, creating an open spot for bonding. When we made a water molecule, the oxygen ended up with 8 valence electrons. The vocabulary word associated to the non-bonded pair of electrons, I have mine top and bottom. This molecule is showing them kind of a top area here. These are called lone pairs. They are not involved in a bond. And if you see a solid line, those are known as bonded pairs of electrons. Here's an electron, here's an electron, 1 shared pair in a bond known as a covalent bond. Why don't we just practice together and get the feel of how to draw Lewis structures? We'll start with some simple structures. Hydrogen fluoride, HF. Well, I remember looking here. Hydrogen has 1 valence electron. Fluorine has 7 valence electrons. So if hydrogen has 1 and fluorine has 7, I'm going to put 1, 2, 3, 4, 1 around each side first, and then assign partners 5, 6, 7, creating this single covalent bond. Hydrogen has achieved a noble gas like helium. Fluorine has achieved a noble gas like its arrangement, which is right next door, is neon. How about 2 fluorines? Well, again, this is pretty predictable. 1, 2, 3, 4, 5, 6, 7 on this fluorine atom. A neighboring fluorine could have 1, 2, 3, 4, 5, 6, 7. And when we draw a line between them, we've drawn a single covalent bond. How about a methane molecule, which is commonly called natural gas? Methane is a fuel that we combust to get out energy. I think symmetry. I have one central atom and the 4 hydrogens will connect back to it. Carbon, who lives in group 4A, here's carbon, group 4A. We discovered that it would have 4 dots, 1, 2, 3, 4, 4 open spots for bonding. And so I'll put 1, 2, 3, 4 dots. See, I have 4 available areas, and I have 4 hydrogens. So I'm going to simply connect 1 hydrogen at a time. 1, 2, 3, and 4. Here is a molecule of methane. Keep in mind, I am not telling you anything about geometry yet. That is a next future lesson. Methane is not a flat molecule. It doesn't lay in the same plane. We will soon learn that it's a tetrahedral molecule. It has some three-dimensional space-filling objects with it. So just keep in mind this is coming. Right now we're just learning about how atoms connect. Let's talk about oxygen. We know oxygen, who lives in group 6A, is a major character in our chapter on ozone, isn't it? Oxygen with 6 valence electrons. And so if we look at oxygen, 1, 2, 3, 4, and I'll just put 5, 6. I see it's going to be connected to another oxygen. 1, 2, 3, 4, and I'll just put 5, 6. I can clearly see where these two can form a single covalent bond, but I'm also getting the sense that I'm not done yet. That this lonely electron and this lonely electron need to form a second bond to achieve an octet. Because right now I just have 1, 2, 3, 4, 5, 6, 7 electrons around each atom. But they all want 8 to be like the noble gas. So you're probably already ahead of me. You're predicting these 2 electrons will come together between the 2 symbols and form what's called a double covalent bond. If I redraw just to show it a little cleaner, a double bond, double covalent bond, is 2 shared pairs, leaving each of these oxygens to have 2 lone pairs so that everybody has the 8 electrons. 2, 4, 6, 8. 2, 4, 6, 8. 2 pairs in a bond and 2 pairs that are lone pairs. What about this ozone molecule, O3? Or I missed over hydrogen. Let's do nitrogen just because it allows me to introduce a triple bond. 1, 2, 3, 4, and I'll just put it here, 5. Because nitrogen lives in group 5, just to remind ourselves how I know that, I'm using my periodic table. Nitrogen in group 5A, we know that it has 5 valence electrons. So there it is with its 5 electrons. And now let's suppose we put it in, hooked to another nitrogen, and I'll just go 1, 2, 3, 4, and I'll put the 5th one here. So I can clearly see here's one bond between the 2 nitrogens. Those 2 will hook together to make a single bond. But visually, do you see how we're not done yet? Lonely, lonely. Let's put them together between the 2 symbols and form a double bond. But lonely and lonely, let's bring those together and make a triple bond, 3 shared pairs of electrons. So to clean that up, you have N, triple bond N, 2, 4, 6, 8, 2, 4, 6, 8 on each of the nitrogens by sharing 3 sets of pairs. There's nothing bigger than a triple bond, by the way. Since ozone is our story, ozone here with resonance, let's introduce this term, resonance. I have 3 oxygens that are going to be placed together. So how might that look? Again, I just want to predict, let me get this. I want to predict the oxygen will be in the center, and I have to hook back the other 2 oxygens. So how many electrons do we have all together? Remember oxygen, who lives in group 6A? So each of those oxygens is going to have 6 electrons. Alrighty, so let's consider how many dots do we get to work with all together. If each of our oxygens has 6 electrons, but there's 3 of the oxygens, we get a total of 18 dots. All right, that's it. How many dots do we get to work with? We get 18 valence electrons. Each of the 3 oxygens has 6 electrons, total of 18. When I connect oxygens back to each other, I've used 1, 2, 3, 4. Giving me a remainder of 14 electrons. I'm going to fill out the octets of the outer elements first. 2, 4, 6. 6 more in this one is 12. That only leaves me with 2 electrons left, and I'll place them on the center atom and then examine what we've built. I have a single bond to the oxygen in either direction. Here's the story, how I know I'm not done. This particular oxygen has the 8 electrons it really wants. 2, 4, 6 in a shared pair, that gets it 8. This oxygen is in the same boat, isn't it? 2, 4, 6 plus the shared pair gets it 8. But what's wrong with this center oxygen? As it stands right now, it has 2, 4, 5, 6 electrons. So it does not reach the octet rule, telling me when this happens, I need a multiple bond. It's my clue that I have to put a double bond in there to get the center oxygen up to 8, but leave the other ones at 8. So let's try this and watch what I'm going to do. Instead of leaving 2 dots right here, and exactly, how come I picked this one? I could have picked this one, absolutely. I'm going to erase a set of dots from the outside oxygen and instead bring them to the center to create a double bond. So this atom is donating both electrons, but something magical happened. Do you see how this oxygen now, it used to have 6, but now it has 1, 2, 3, 4, 5, 6, 7, 8. It has satisfied the octet rule by creating a double bond. This guy still has 8, this guy has 8, and this guy has 8. So what we've ended up drawing, just to kind of clean it up, I have oxygen with a double bond to one other oxygen and a single bond to the other oxygen to make an ozone, an allotrope of oxygen molecules. Now let me introduce this word called resonance. Do you remember a moment ago when I said, why am I picking this oxygen to create the double bond? I absolutely could have selected the other oxygen to make the double bond. And when I do, I'm creating what's called a resonance structure for that particular molecule. And what you'll see is them designated with an arrow with a head on both ends. So that's a double-headed arrow. These are equivalent structures. The term resonance isn't just taking this molecule that we drew here and just flipping it over so the double bond's the other way, but it's actually saying, well, let's suppose this oxygen is in the same position, it's the same oxygen, and this oxygen is in the same position. It's not just flipping the molecule, but it's taking the actual bond and moving it from one position to the other. They are equally correct structures known as a resonance structure. What about H2s Hydrogen Sulfide? Again, think symmetry. Who's going to be your central atom? And in your central atom, never pick hydrogen. So if I find my periodic table, here it is. Sulfur, who lives in group 6A, is going to have 6 valence electrons, just like oxygen did when we drew it down here. And so if I continue with those samples, I want to hook H2s together. I'm going to put sulfur in the center, and notice how it has 6 dots. And I would attach each hydrogen in those empty spots for bonding. There's your compound, H2s. And maybe just one more, since we have a chlorofluorocarbon, which are those pollutants that destroy the ozone molecule. I would know to place carbon in the center because it has 4 valence electrons. Those 4 valence electrons will serve quite nicely for those four atoms of 2 chlorines and 2 fluorines to actually attach to. Remember symmetry. If I'm going to select a central atom, pick the one you just have one of. You have 1 carbon, build back to it. Now, of course, each of the halogens lives in group 7A, so you'll just finish those dots. There's a single covalent bond. Fluorine, who lives in group 7A, will form a single covalent bond. Same here with the chlorine, group 7A, single bond. And this fluorine, also in 7A, a single bond. I've created a symmetrical molecule with 4 single covalent bonds. Everybody has the octet rule. We've introduced the idea of multiple bonds. We saw how oxygen, the molecular oxygen O2, actually forms a double bond with its 6 valence electrons, so that both of those end up with 8. So 2 shared pairs represents a double bond. Here's a molecule. This is acetylene, C, triple bond C, single bond H. This is called a triple covalent bond, which is 3 shared pairs. There's nothing bigger than a triple, we've already mentioned. We've introduced the resonance structure, resonance form. Here I have a central atom of nitrogen. Notice here I have nitrogen in the center. That stays in a fixed position. I also have oxygens, and what I'm trying to do is color code. The oxygen in yellow stays in the fixed position. The oxygen that I'm putting around with a black circle is staying in a fixed position. And the oxygen I'm putting around in a solid purple is staying in a fixed position. What is moving from picture 1 to picture 2 to picture 3 is simply the location, and let's kind of clarify, it's the location of where that bond is. Here is where the double bond is between nitrogen and this position 1 of yellow. Here is the double bond. It's going up to the second purple oxygen. And here we see it moving to this third scenario where it's going to the other oxygen. We're not rotating it, we're actually moving the double bond between nitrogen and a different oxygen atom. These are all equivalent structures. They're all correct. So we see this double-headed arrow showing structure number 1 is exactly equivalent to structure number 2, who's exactly equivalent to structure number 3. They are known as resonance structure. Resonance, where I can have a multiple bond going in any of the other directions and have an equivalent structure. So let's take a look at some homework questions, see if we can't process together some of our answers. Match each term to its description. Well, the terms are lone pair, single bond, triple bond, double bond. Let's see if we can't match the definitions. Made up of 2 unshared electrons. They're shown as 2 dots in a Lewis structure. So if I'm just kind of figuring out what they're saying, that's the part of the structure they're looking at. 2 unshared electrons, we know that to be called a lone pair. made up of 2 shared electrons and shown as a line between 2 atoms. It's this right here. 2 shared electrons. So here's one and here's one. A shared pair is what we would refer to as a single covalent bond. Made up of 4 shared electrons and drawn as 2 lines. So we would see this as what we refer to as a double bond. 4 electrons because each line represents a shared pair. And of course 6 shared pairs would look like this. We'd have 1, 2, 3, 4, 5, 6 electrons all being shared and denoted with 3 lines. There's your triple covalent bond. Consider this structure. We have sulfur in the center, single bond oxygen to the right, single bond oxygen to the left, double bond oxygen down. Count the number of shared, or what we would refer to as bonding, electrons. How many electrons are in bonds? Well, if we highlight, this bond represents 2 electrons. This bond represents 2 electrons. So do these. 2, 4, 6, 8. 8 electrons that are in shared pairs. How many unshared electrons do you see? Unshared electrons. Well, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 dots around that symbol. Getting a little crowded there. How many shared pairs of electrons? Well, if there's 8 electrons, how many pairs is that? And again, you could see it would be 1 pair, 2 pair, 3 pair, 4 pair. 8 electrons is 4 shared pairs. Unshared pairs of electrons. Well, if there's if there's 16 unshared, that would give us 8, and we can count them. 1, 2, 3, 4, 5, 6, 7, 8 shared pairs of electrons. Total number of valence electrons in the structure. Well, how many total electrons do we have? We would take the number of bonded electrons, which we determined to be 8. Let's write something a little bit better. I'll write 8 in a solid line. There's 8 electrons that are in bonds. There's 16 electrons that are non-bonded, and if I just simply add, I would know there's 24 total electrons. The sum of all of the electrons is 24. What element would we never, ever, ever select to be the central atom? We know that to be hydrogen, and we know that because hydrogen only has 1 electron, so it really only has 1 connection. Carbon, who lives in group 4A, I like him. He's got 4 open spots for bonding. Oxygen, I could select that because I could still have 2 open spots for bonding, and so forth. Hydrogen I would never select because just 1 spot, and then I can never connect anything back to it. Let's complete these structures by adding dots. I have HF, just to kind of get an idea if you can't read it. HF. Hydrogen lives in group 1A. It has 1 valence electron. Let's make it red. Fluorine lives in group 7A. It has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. To complete this structure, I need to place 2, 4, 6 dots as 3 lone pairs. pair. How about this guy? This looks like a water molecule, doesn't it? H has one valence electron, lives in group 1A. Oxygen has 6 valence electrons. It lives in group 6A. So 1, 2, 3, 4, 5, 6. Of course, those are the solid lines representing covalent bonds. So to finish the water molecule, we have to add 2 lone pair on the oxygen. What do we got going here? We have ONH. Of course, hydrogen has just 1 electron, so that's already involved. Nitrogen has 5, so let's draw them in. 1, 2, 3. Now it looks like it needs 5, so I'm going to add a lone pair on top of nitrogen because it lives in group 5A. It has to have 5 electrons assigned to it. 1, 2, 3, 4, 5. An oxygen who lives in group 6A has to have 6 dots assigned to it, and right now it only has 1, 2, so I have to go 3, 4, 5, 6. I'll clean it up. Oh, I can make that one big electron. We have O, double bond N, single bond H. To finish the structure, we have to make sure that each atom has a noble gas arrangement. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. It now has an octet. Hydrogen only needs 2, 2, 4, 6, 8 on the oxygen. We've obeyed the octet rule for each of these molecules by adding in the missing dots. We'll look at another homework for you. These are green bonds, and what it's telling us is click on the bonds to change them from double to triple as needed. And if the bonds already connect, just ignore it. So here's what I noticed. Carbon has 4 valence electrons. Alrighty, so it needs to have either 4 electrons or a multiple bond to get an octet. What I like in this picture, carbon has 2, 4, 6, 8 electrons assigned to it. By having those single bonds, this guy is done. Leave it alone. But what about here? I have 1, 2, 3 electron bonds around this carbon. To finish it, we're going to need to add a double bond to get the carbon that it needs to have 4 bonding atoms. 1, 2, 3, 4. And you might have predicted, what must this have in order to get carbon to have 4 bonds that it needs to fill its octet? It has just 1 out there. We're going to need to draw a triple bond so that each carbon has the 4 bonds it needs to give a valence of 8 electrons. We went from single to double to triple. What's wrong with this structure? Let's kind of look at it. I have O, and then I have a single bond. Notice it's just 1 shared pair of electrons. So this is the structure, just drawn bigger so we can examine it. I know that oxygen lives in group 6A, so it has 6 electrons, and I know that there's 2 oxygens there. So that only gives me 12 electrons. It's only 12 dots that I get to use. How many does this structure have? If each of the oxygens can contribute 6 valence electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 14 dots in this structure. I'm only allowed 12, so I can see the number of electrons. Well, that's not right. So I have too many dots in the structure. To get the oxygen to have an octet with only 12 electrons, that's how we introduce the double bond. Here's the oxygen double bonded to an oxygen to create an octet, but it's done with only 12 electrons. And we'll look at one more. Let's look at C, H2O, which is an embalming agent. It's known as formaldehyde. We're going to put carbon in the center. Carbon is the element with 4 valence electrons. I know that I can place a hydrogen with its 1 electron and just kind of take care of these spots that are open. And I also know, and I'll switch colors here, oxygen will attach back, and I'll have 1, 2, 3, 4, 5, 6. So there's a bond. Here's a lonely electron. There's a lonely electron. I see that I can predict that we'd have a double bond between the C and the O. So just to redraw, kind of clean it up a little bit after I've moved electrons around, I have C, single bond H, double bond oxygen, and now we have the correct number of electrons attaching back to the center atom, carbon. Carbon dioxide, this is interesting. We can hook back to the carbon, the central atom. So I'm getting just an idea. Carbon, I can just kind of do this with you. We have carbon with 4 valence electrons, lives with group 4A. We know oxygen has 6 valence electrons, it lives in group 6A, but there's 2 of them. So all together I get 16 dots, which the dots represent electrons. And so far, out of the 16, just by connecting the oxygens back to the carbon, I've used 1, 2, 3, 4, leaving me 12 remaining. Fill the octet of the outer atoms first. And when I place the octet around the oxygens, there's no dots left. They're all gone. And yet I understand that the carbon does not have an octet. The structure isn't done, but I don't have any dots left. That's how I know that I'm going to need a multiple bond. Not just singles. Oops, that's supposed to be a B. A multiple bond. So watch what I'm going to do. See these 2 electrons here? I'm going to bring them up and make a double bond. See these electrons here? I'm going to bring them up and make a double bond. So now, by forming a multiple bond, I can get the carbon to have the 8 electrons it needs, and notice how I did that, a shared pair, so 2, 4, 6, 8, that gives carbon an octet of 8 electrons. And it's going to give 2, 4, 6, 8 for this oxygen, and 2, 4, 6, 8 on that oxygen. By forming a multiple bond, we've created an octet for every atom. And I know that these might be brand new skills, but we just get a hang of it and you'll start to see a pattern. So when I begin, if I want to draw a molecule of CO, which is called carbon monoxide, a product of incomplete combustion of fuels, carbon monoxide. Carbon lives in group 4A, so it has 4 dots. Oxygen lives in group 6A. It has 6 dots. So the number of electrons I get to use is 10. No more, no less. I have only 10 dots. And out of that, I've got to try to satisfy the octet rule for each one of these atoms. So I connect them together, and that uses up 2 dots, leaving me 8 left. And I could go 1, 2, 3, 4, 5, 6, 7, 8, thinking symmetry. And now I'm done with dots. There's nothing left. And yet, I know I'm not done because I don't have an octet yet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So each of these elements only has 6 electrons. That's my clue that I'm going to need a multiple bond. And so, let's suppose, and for no particular reason, I'll take these 2 just because they're close. I'll put them in the center. Same idea here. I'm going to take these 2 and bring them to the center. And when we did that, we just made what's called a triple bond. Let's just clean it up. C, triple bond O, leaving me one lone pair on each of those symbols. C, triple bond O, lone pair. And now we can count 8 electrons on each of those atoms. We obeyed the octet rule with the triple bond. Here's carbon with its 4 valence electrons. I can put a hydrogen right here and have that all set. So this side looks good. We'll have a nitrogen. Nitrogen who lives in group 5A, remember? 1, 2, 3. And then if I did 4, 5, I could see a bond forming here. Then you get a nice little visual of how this lonely electron and this lonely electron form a bond. This lonely electron and this lonely electron form a bond. Cleaning it up, you get H, single bond C, triple bond N with its lone pair off to the side. You're doing such good work. And if this is a brand new skill, keep with it. You're doing amazing. This looks like a resonance structure. Are you picking up on how I know that? Here's a central atom, carbon. Here's a central atom. And what's different is the location of the double bond. Perhaps I'm going to the double bond up top, or perhaps I'm going this way. But everything is identical except the location of the double bond. It's going up to the oxygen towards the right, or it's going up to the oxygen towards the left. These are what we refer to as equivalent structures, and that's why we see the double arrowhead. So the actual structure of formate switches back and forth. That's not true. It's actually both structures at the same time. So the term resonance structures means that it's a carbon-oxygen bond somewhere between the single and double. So if I were to really show this, I could have oxygens, hydrogen, and instead of having a double bond in just one direction, let me make that a better line. What we're really showing is a dashed line on purpose, a dashed line between the two oxygens. It's not quite a single, it's not quite a double, but it's in between the two in terms of length. It is what's referred to as a delocalized electron bond. That the electron density is not just in one direction, but it's equally distributed in both directions. Distributed. So I think of it as a hybrid between these two. It's not one or the other, but a blend of both all at the same time. You have done fantastic work. Let's pause the video lesson here, kind of process and digest with your reading, and when ready you have one more video lesson to come back to complete your chapter. Good work, team.